I've decided to make some videos which will use ideas taken from the philosophy of Tathagata Zen Buddhism in order to intuitively reinterpret special relativity and quantum mechanics. In so doing, I hope to create a new approach towards explaining such diverse mysteries as the measurement problem, quantum gravity, and human consciousness. I am not a scientist. Therefore, please try to take all of the following videos with an open mind and more than a pinch of salt. They are intended to be simply an out-of-the-box, extended philosophical thought exercise, asking the question, could it possibly be this way? If any of my conjectures end up making some small degree of sense, either to scientists, Buddhists, or anyone else, then I will have considered my time to have been well spent. If not, well, at least I had fun doing it. This first video will outline the basics of this approach, which I have dubbed the Zen interpretation, and apply it to the topic of electromagnetic radiation, otherwise known as light. A brief introduction to the basics. Albert Einstein revolutionized our understanding of time and space when he discovered that the causes and effects of any event couldn't travel faster than the speed of light. These ideas were first published in 1905 as the special theory of relativity, which will be referred to as SR. One of the most useful and common tools for illustrating SR's description of causality is a Minkowski space-time diagram. The Minkowski space-time diagram simply shows how fast any event can be caused by or affect anything else. This speed limit of causality is the speed of light. Each light cone diagram illustrates a particular inertial frame of reference oriented to a specific event or sequence of events. An inertial frame of reference is just a system of things traveling together at a constant speed, with no acceleration at all. Differing inertial frames of reference are often compared to each other in order to help illustrate the relative differences of time and space perceived between them. That is, in order to maintain the constancy of the speed of light between different frames of reference, the physical measurements of both time and space will change accordingly. A Minkowski space-time diagram can be divided into four main parts: the past light cone of an event, the event itself, the future light cone of an event, and all of the remaining space-time outside of both the past and future light cones of that event. The past light cone of an event represents the history of all the previous causes of an event. Of course, these causes were only able to move at the speed of light or slower. The future light cone of an event represents all of the effects generated by a particular event, and whose progression is, again, limited by the speed of light. The event itself in SR is represented by a point particle. A point particle is a conceptual representation of an event, whose size, shape, and structure are irrelevant to its given relativistic context. For example, even a galaxy can be considered to be a point particle within the relativistic framework of SR. When the history of a point particle is plotted through time and space, a world line is formed, with each point along the line having its own past and future light cones. The fourth part of a space-time diagram includes everything outside of both the past and future light cones of an event, existing in what is commonly referred to as an unknowable or causally disconnected state called a space-like separation. SR makes clear that when something is in a state of space-like separation from a particular event, it can have no causal influence on that event whatsoever, because in order to do so, that influence would have to travel faster than the speed of light. A classic example of this is that it takes light leaving the sun about 8 minutes to reach the Earth. Until that light hits us, according to SR, the Earth and Sun exist in a state of space-like separation and can have absolutely no causal impact on each other. However, there was another extremely well-proven theory which suggests that the conclusions of SR don't explain exactly how things work at the very small scales. That theory is called quantum mechanics. Soon after Einstein published his work at the beginning of the 20th century, it was posited by others that at the quantum level of interactions, causal influences don't adhere to the rules of SR. These type of phenomena express a peculiar type of behavior generally referred to as quantum non-locality. The assertions of quantum mechanics have been mathematically verified and re-verified many times. Regarding one of the most baffling expressions of non-locality, it was experimentally shown by Alan Aspect in 1982 that it is possible to split certain fundamental particles into two oppositely polarized subparticles. If these subparticles are separated by some distance, and only one of them is changed, its opposite half instantaneously reflects an equal and opposite change regardless of the distance between them. This is indeed a mysterious thing, because in order for one of the subdivided particles to instantaneously influence the other, it would seem to challenge the rules of special relativity, defining space-like separation. That is, according to SR, two entities in a space-like separation should not be able to have any causal influence on each other, but they do. This spooky action at a distance, as it was labeled by Einstein, is a property of quantum non-locality called quantum entanglement. Furthermore, even the mere act of observing one of the separated subparticles is enough to change its other half. Trying to find a way to reconcile the theoretical disparity between the classical level causality of SR and the spooky behaviors at the quantum level has proven to be very difficult and persists even today. Up until a couple of decades ago, a shaky peace had existed between these two great scientific theories. The Copenhagen interpretation argued that the instantaneous transfer of influence at the quantum level belongs to another level of reality entirely and has little or no direct corollary in the non-quantum or classical level everyday world. Why is this instantaneous influence evident at the quantum level, but not at the classical level? Is it truly, as is posited in the Copenhagen interpretation, because the quantum level operates by completely different rules? Or is there some other, more principled explanation? Of course, an even more profound question is, at the quantum level, how is an instantaneous influence brought about through the mere act of observation? What role does observation play within such causal processes? Is it merely as a passive, uninvolved witness? Or does it somehow play a more fundamental role in dictating the effects of quantum-level interactions? Whenever using a Minkowski spacetime diagram, one must always assume the role of a detached observer. That is, there is no possible way to represent the action of observation within such a spacetime diagram. For example, if we assume that an observer is a point particle, then it could have no access either to its past or future light cones, and so it could not compare its relative state over time. In the Minkowski spacetime diagram, an event's representation is limited only to an eternal now. On the other hand, an observer can't be depicted in a state of space-like separation from an event, because by definition, no information about that event can reach it, thus rendering observation impossible. Until we create a spacetime diagram that can represent the function of observation within the framework of that diagram, we must continue to accept observation as a necessary yet inexplicably assumed constant. A different approach. Special relativity holds that everything moving at the same speed, that is, in a shared inertial frame of reference, shares the exact same relationship relative to the speed of light as any other. That is, no single inertial frame of reference is correct relative to any others. If this is true, then it logically follows that the fundamental laws of physics do not vary between inertial frames of reference, although they must all respect the universal speed limit. Thus, in special relativity, much focus is put on explaining the relative differences which occur between different inertial frames of reference, precisely because they must obey the universal speed limit, which is the speed of light. Although depicting events as point particles works wonderfully well when used to make relative comparisons between two or more frames of reference, it may not be the best approach when trying to describe the intrinsic nature of a single event. So, in a perfect inversion of Minkowski's model, the approach taken in the Zen interpretation, which I will call ZI, will be to completely ignore the relativistic differences between inertial frames of reference and instead focus on the isolated internal dynamics necessary to form any single event. Here, events are no longer represented as isolated and distinct point particles, but as evolving space-time relationships defined by an ever-changing set of conjugal, space-like separated conditional inverses. That is to say, at this exact instant, the center of our bodies is in a state of space-like separation from our outer extremities. Of course, our inner and outer extremities will inevitably interact with each other, and it is only through this interaction or information that our bodies can continue to function as evolving three-dimensional historical entities. We can depict this relationship as a particular circle relative to its exact center. Just as the inner and outer limits of our bodies interact, the circumference of a circle and its center will continually progress to their opposite extreme and back again. This simple diagram can be used to model the historical progression of the formation, maturation, and decay of any classical level interaction. This is the ZI version of a space-time diagram, governing the formation and decay of events. Ultimately, by extension, this approach will provide a way to begin to bridge our experience of subject and object, that is, the subjective experience itself, without mistakenly assuming it to be a discretized objective entity point particle. Using this approach, a map will be traced through both decreasing and increasing orders of complexity, so that eventually the function of consciousness can be modeled within a diagram rather than taken as an assumed external constant. In order to more thoroughly understand the ZI spacetime diagram, a simple set of postulates can be introduced. First, all systems can be described as a pair of space-like separated conditional inverses. Second, all conditional inverses continuously change with respect to each other by cycling between states of relative unity and polarity. If all events can be understood in terms of a pair of conditional inverses, then the simplest hypothetical expression would be two things which, when taken together, would include all of time and space. For example, that table in front of you is the perfect and unique inverse of everything that is not that table. Whether a table is bigger or smaller than another, or whether it existed 100 years ago or in the present day, is irrelevant. This is because all such variations serve only to further define the unique and perfect contrasting relationship between that particular table as a subject and the totality of its uniquely corresponding context. Of course, such codependent polarities are not only limited to such an extreme example as a particular entity contrasted to the rest of time and space. Any more localized system can also be internally subdivided into a set of conditional inverses, which function together as the total system. For example, the aforementioned table can be divided into a left side and a right side, or a specific period of time can be divided into the beginning half and the ending half. As localized events become more and more complex, the conditional inverses capable of describing them need not be limited to only one pair. That is, there are many different ways to divide a table into conditional inverses, depending on which of its many properties one chooses to focus on. We can divide it into left side and right side, top or bottom, or one leg as opposed to the rest of the table, etc. The point is that most macro-level objects are so complex that we lose sight of the fact that our objective experience of them arises as the product of many A and non-A relationships, which we unconsciously synthesize and subjectively reduce to a particular thing in contrast to everything which is not that thing. A good analogy for this is found in Gestalt's famous figure and ground images. That is, before anyone is looking at the black and white parts of the image, they exist in a relatively pre-informational state, devoid of any provisional meaning. It's not until an observer synthesizes the black and white portions into a specific subject and object context that the provisional information about their relationship comes into being. That is to say, the conjugal opposites of figure and ground intrinsically define each other even before they have been extrinsically synthesized by a viewer into a provisional subject and context. It is only after their interaction, which in this case takes place within the mind of some observer, that they are given the provisional roles of subject and corresponding context. Thus, although it is necessary to have a human mind to extrinsically synthesize a Gestalt image into a provisional subject and context, the purely intrinsic information of the physical image itself doesn't require a human mind to exist. To put this principle into some active examples, the aforementioned table cannot be moved forward even the smallest amount without the context within which that table exists simultaneously changing in some uniquely corresponding way. Whether or not anyone is there to see that movement is irrelevant. The same is true of any bit of light leaving the sun relative to its space-like separation from the Earth, as well as any instantaneous influence we might observe between entangled particles. So, entities in space-like separation share an instantaneous creation of information between them. It's just that all such information is intrinsic rather than extrinsic. And just as was theorized by Einstein, that information can only be extrinsically conveyed from point A to point B at the speed of light or slower. Time is light. If, according to postulates, all conditional inverses must continuously interact, and that interaction can be described as an alternation between states of relative unification and polarization, what happens when a set of conditional inverses expresses the most simple system possible? One real-world example of this, what ZI terms a first-order complexity, is a single photon in relationship to the rest of the universe. That is, from the ZI perspective, a photon-universe pairing is the most fundamental system of conditional inverses possible. This pair of conditional inverses can also be thought of as corresponding to the electromagnetic wave model of James Clerk Maxwell, where the electric field represents the individual photons, A, and the magnetic field, its conjugal opposite, that is, the remainder of the cosmos, non-A. Thus, the oscillation of the electric and magnetic fields is like the cyclical alternation between the unity and polarity illustrated in the ZI cycle of change. Of course, the rate at which an electromagnetic field can propagate is limited by the speed of light. In fact, it is the speed of light. A photon and its universal context would naturally define the totality of the universe. Thus, there is no spatial distance between them. Why? Quite simply because when there is nothing other than a single photon in contrast to the rest of time and space, what is left to put between them? To make more sense of this, we can ask a simple question. What is space in and of itself, apart from being the product of time and velocity? That is to say, any formulaic definition simply kicks the can down the road to another set of variables. Therefore, distance is defined in Zi as some mutually informed relationship formed by the interaction between a pair of conditional inverses. Just like the way two walls of a canyon are necessary to continuously define the space formed between them as a canyon. If you take away one of the walls, the space between them loses its provisional definition. However, in the case of a photon, as opposed to everything which is not that photon, they do not exist as objects within a larger context, and so they can never truly be separated from each other. So, although their relative degree of polarity and unity does indeed vary as they alternate, no distance, that is to say, no provisional space, can ever be formed between them. Thus, in the Zi model, there is no spatial dimension to light, only a temporal one. One might imagine this model of light as being like a metronome as opposed to a wall clock. The metronome has no internalized way to further organize its rhythmic cycling beyond the sound itself. It merely oscillates from left to right, back and forth, making the same sound over and over again. That is, without some way to relativize each moment, such as the distance traveled by hands moving around a clock, time operates without the need for space. However, it cannot operate independently from some set of alternating conditional inverses. Albert Einstein once was asked, "What is time?" To which he famously replied, "Time is what you measure on a clock." One might say that Zi disagrees with this and rather describes light as time rather than something that occurs in time. Thus, in contrast to the answer given by Einstein about time being what you measure on a clock, Zi would reply, "Time is light." What might make this statement seem more plausible is to remember that it's not only the photon which is defined when it polarizes from the cosmos, but also the cosmos which is defined as it polarizes from the photon. And what aspect of the cosmos is defined? Its definitive rate of change, also known as time. One might think of it as the birth of diversity itself, but a state of diversity in which no in-between state has been formed, only time. Seen this way, light can be understood as the eternally intrinsic heartbeat of the universe, upon which all other rhythms, tones, or melodies must be oriented to and assembled from. Thus, as strange as it might seem, Zi postulates an equivalence between time and light. Looking at the phenomenon of light this way offers some startlingly simple ways to understand the unique properties of light at both the quantum and classical levels. That is, although the direction and speed of a photon cosmos polarity can be measured and verified as a wave function of electromagnetic radiation, the individual photons themselves can never be identified while in the state where they are actively cycling with the cosmos as a whole, that is, as a wave function. It's an all or nothing deal. Either the photon-cosmos pairing is fundamentally defined by its relationship to the cosmos as a whole, or it functions as a relativized component of some other higher order system of conditional inverses embedded within the cosmos. Therefore, although certain types of interactions, like gravitational lensing, can exert influences on a freely moving photon-cosmos pairing during the polar states of their oscillation, the system remains fundamentally defined by their conjugal relationship until such time as it is superseded by another, involving, for example, the photon striking some bit of photosensitive film, or perhaps a banana leaf in some jungle. Thus, when a freely moving photon exists in an exclusive relationship with the rest of the cosmos, it stands to reason that no matter how fast any particular set of macro-level eyes within the cosmos are traveling, the speed of light seen by those eyes will always be the same, because that light is being defined by its global relationship with the cosmos rather than to the localized condition of the eyes. One could paraphrase John Donne's famous lines from Devotions Upon Emergent Occasions to read, "Ask not from what the beam of light is bursting forth from, nor be concerned with the speed of its origin, for it bursts forth from thee." Therefore, as Einstein so brilliantly discovered, the speed of light is constant for every inertial frame of reference, and each adjusts its own expressions of localized time and space in order to reflect the fundamental nature of light as time. Given the above model, we can now apply it to the problem of quantum entanglement. Quantum entanglement is exhibited when a micro-level particle in a quantum superposition is divided in such a way that each shares both of the two possible directions of their angular momentum, or spin. This can be thought of as each subparticle being both spinning up and spinning down at the same time. What is even more fascinating about quantum entanglement is that once the actual direction of the spin of one of the entangled halves is determined, the other half immediately expresses only the opposite direction, regardless of the distance separating the two halves. The superposition enjoyed by both collapses. This mysterious and simultaneous action at a distance between the divided halves seems to contradict, or at least stretch, Einstein's discovery about the transfer of information being limited to the speed of light as set forth in special relativity. However, once we assert that so long as any particle involved in a wave function is also engaged in a polarity unification or relationship with the totality of its context, then even if a superficial splitting of the particle into two halves occurs by some relatively minor interaction, the integrity of the defining relationship remains intact. Thus, even though we, as macro-level beings, can measure a relative distance between the two entangled halves, at the intrinsic level of that particle context system, that distance is meaningless. That is, as discussed above, ZI posits that for freely moving quantum-level particles, relative distance does not exist. There is only the polarizing and unifying of that particle with the totality of its context, with no distance formed between them. It isn't until one of the subparticles becomes involved with some macro-level interaction, which is strong enough to reorient the particle to its own level of complexity, that the quantum level superposition, that is, its wave function, collapses. However, the quantum level particle doesn't suddenly become a macro level entity. Rather, it's simply that the conditional inverse of that particle has changed from being the totality of its global context to that of being a more locally defined context. Seen this way, everything at both micro and macro levels can be understood as a wave function, the only difference being the level of complexity created by each entity context system. When we apply the ZI model to the double slit experiment, it gives us a wonderfully simple explanation for the observed wave-particle duality. As Richard Feynman showed in quantum electrodynamics, or QED, all the opposing probabilities for where a quantum-level particle will polarize from the rest of the cosmos at a particular time can be added up in such a way where the opposing probabilities cancel each other out, leaving the remaining probability for that particle to behave in a certain way, although the exact time and location of that behavior will always be ultimately random. This is an expression of quantum indeterminacy. Thus, we can determine the probability that a quantum level particle will be observed in a particular place, but it can never be precisely determined when it will happen. This quantum indeterminacy is always graphically represented in the ZI cycle of change by the gray circle. This built-in randomness in the ZI model is important in order to be able to understand the double slit experiment. Given the ZI explanation for the nature of entanglement, a quantum level particle's interaction with the double slits becomes crystal clear. That is, as the quantum level particle passes through the two slits, that interaction isn't sufficiently intense enough to collapse the particle out of its defining wave function. Rather, in passing through the two slits, a subtle influence takes place, in which the particle context system transforms into superficially divided halves. Of course, as explained earlier, the entangled subparticles still share their single relationship with the totality of the global context. As such, their corresponding wave functions also express this strange subdivided nature. Thus, it appears to us as though two wave functions go through the slits, when in reality it is a single wave function corresponding to only a single pair of conditional inverses superficially divided by circumstances. These entangled parts of the divided wave function then interfere with each other after they go through the two slits. As the wave function interferes with itself, crests and troughs are formed. These strike the final detector screen, and the original photon is finally wrested from its entangled global relationship and is reoriented into the more localized context of the detector screen. Thus, the original wave function collapses and a mark is left on the detector screen. Which of the crests formed by the interference pattern will be the one where the particle collapses onto the detector screen cannot be predicted, and is an expression of quantum indeterminacy. When the test is run many times, an interference pattern is formed corresponding to all the places where the crests of the wave created by the superficially divided wave function occur. Of course, it almost goes without saying that if the wave travels only through a single slit instead of a double slit, then there is no interference pattern created. The particle is detected on the detector screen, primarily at the crest of the impending wave as it hits it. Since a single wave function shot through a single slit won't interfere with itself, it won't create an interference pattern. This is the basic Zen interpretation for explaining entanglement in the collapse of the wave function. Of course, we still have not begun to discuss the role of observation in collapsing the wave function, but that requires further modeling of the ZI cycle of change. Videos explaining this will soon follow. If you have found the ideas in this first video about ZI interesting, please consider subscribing to my channel. In my next videos, I will further develop the ZI cycle of change in order to try to develop an intuitive explanation for subjects as diverse as the fine structure constant, mass, gravity, as well as human consciousness. Stay tuned.